So it's my honor to introduce Professor R. Srikant from UIUC. While I believe an introduction to Srikant is unnecessary to this audience, but I want to mention two personal experiences of him. I remember when I was a student working with Stephen, whenever I would travel to InfoCon or Adelaide conference, Stephen always told me, do find a chance to talk to Srikant. So this is a testament to their academic fellowship and friendship. Additionally, I have had the privilege of seeking Srikant's support as a reference on multiple occasions. Srikant has always been very kind and generous supportive of me. So I believe many of our Stephen student and postdocs share similar experience. So today, Srikant is going to talk about his exciting work on learning and control of countable state spaces.
Thank you, Legion. It's my pleasure to be here, pleasure and honor to be here, part of celebrating Stephen Lowe's great career. I've known Stephen for a long time. In those days, they didn't even have color photos. So I guess we first met maybe around the time we were in Bell Labs, and it looks pretty much the same, except the photo is colorized. Happy birthday, Stephen. Happy fake birthday, at least. I guess it was in March. It's been great to know you as a colleague, friend, and an inspiration in the area. I'll start out by saying a few words about Stephen's work. I think it was 1997 GlobeCom, maybe, in Melbourne. When I happened to be at GlobeCom, and I went to Stephen's talk, and I think this might be one of the first times you presented this work, or one of the early times you presented this work with Lapsley. And the great idea was formulate network resource allocation problems as an optimization problem. People had these various words for resource allocation. Practical networking people would call it protocols, theoretical CS people would call them algorithms, but they were all sort of done in an ad hoc fashion. I mean, you look at each particular component of the network, like you look at the router, you look at the switch, you look at the link, you look at 3 links at a time, and there were all these different methods for studying network protocols and algorithms. And what I was struck by when I was listening to Stephen's talk was this beautiful idea that connected. To me, this is sort of something that's resonated for a very, very long time, and it's now crossed over to other areas, by the way. So the idea is this. So you think of a constraint and an optimization problem. I mean, any resource allocation problem, you have a resource allocation problem in the first place because there are constraints, right? So you have a constraint of the form y less than or equal to x, and Stephen and Lapsley's idea was to think of it as a queue. So what is y less than or equal to x? If you have a queue, and y is the arrival rate of whatever thing that goes into the queue, like packets, for example, and then x is the departure rate, then this constraint is satisfied if this queue is stable. This constraint is not satisfied if the queue is not stable. This is a brilliant idea. It's connection between constraint satisfaction and queue stability, queues and Lagrange multipliers. By the way, this queue length are also the same thing as Lagrange multipliers. This connection is an incredible connection, and it's sort of made analyzing networks beyond a single node and looking inside a router, just looking at the network as a whole is just profound, and it's so big that I feel like people outside the communication networks area now use it. So whenever there's a constraint, people think of it as, okay, how do I make sure the constraint is satisfied? I'll keep some sort of a token bucket and put tokens into it at the rate y and remove tokens from it at rate x. And many of these people don't even know this idea came from Stephen, which I think is the hallmark of a great idea. It's just permeated, people in machine learning conferences now use this idea, and it's profound. And it's got a lot of implications. I think one of the main implications of it is because you're able to look at it as the network as a whole, it has architectural implications, and I don't have the same verbal dexterity as John, so I'll leave it up to him to talk about it during the banquet speech. I'll focus on a more narrow contribution as a modeling abstraction. I think most of you probably have seen this quote by George Box that says all models are wrong, but some are useful. It's an overused quote, but I think it's very accurate. So here are two abstractions. I mean, there are many, many things here, but there are two abstractions. Packets are discrete entities. In a communication network, you're sending packets, like each one of them is so many bytes or whatever, right? But model them as fluids. I mean, modeling them at the packet level would have been just made it impossible to understand networks as a whole. And the second thing is buffers are finite. I mean, in the early 1990s, before Stephen's work, you could see a lot of papers talking about, oh, you know, there are this many packets in the buffer, they're arriving one at a time, and, you know, doing detailed analysis and so on. But model them as infinite. I mean, these two are both incorrect, but profoundly beautiful and abstracts the problem away and making it accessible to a much larger audience. I mean, brought in control theorists, optimization theorists, networking people, and so the power of abstraction is something that's beautiful in Stephen's work, and I think it also has an implication for architectural impact of Stephen's work, which John will talk about this evening. Okay, so with this introduction, let me move on to my talk. So I'm going to talk about learning and control in countable state spaces. So I'm going to try to give Stephen Low style infinite buffer fluid queue intuition for what I'm doing. But for some of the problems that we need to look at, we need to look at the first abstraction. I do think that I should probably be able to get rid of the packets as discrete entities and model them as fluids. I've not been able to do it so far. So I will, towards the end, I'll wrap it up. When I wrap it up, I'll tell you why I think just a purely Stephen Low style analysis should be possible. But for the purposes of this talk, I need to think of discrete queue lengths, and I'll talk about why I do that and give you some examples of problems where this arises. So this is the work of Yashashwini Murthy, my brilliant student. She's just absolutely awesome. And Izzy Grosov, who's my postdoc, who's also outstanding. Izzy will be joining Northwestern as a professor this fall. And Sivateja Magaluri, with whom Izzy is a joint postdoc. Okay, so this talk is about reinforcement learning applied to networks, but not in the way that you normally see it. I'll use a lot of abstractions, and I think that's the connection to when I talked about abstraction that Stephen uses in his work. I'll talk about why these abstractions are useful. In particular, why one shouldn't just do machine learning just without exploiting problem structure. I think being control theorists, we all know that often problems have some structure. Even if they don't have structure, we impose a structure. We approximate it by a linear system, for example, and this has been greatly successful. And my point in this talk is going to be there's some structure, even if it is very little in certain types of networks, you should exploit it. And that's what will give you good algorithms. And if you don't, if you just blindly apply reinforcement learning techniques, you won't get it. So these are some of the examples of reinforcement learning techniques, reinforcement learning applications, but mostly they've been applied to problems with little structure, or people don't think about the structure in the problem, like chess, for example. It's very difficult to, there's no proper topological structure for chess. So each state is just a state, and then there is some in chess, there is no probability, but I think for example, in other types of game playing, there's a probability of you take an action and there's a probability that the state will move to a different state. So this kind of problems are studied using the theory of MDPs with no structure. Other extreme, I think, is machine learning has also gotten into control theory a little bit. I think historically, we used to call it system identification. And now the same thing is sometimes called machine learning. So system identification followed by control has been done in the control theory literature for a long time. But there are also new things like policy optimization is something that people are studying. So for a linear system, the optimal solution is linear, and so you try to find the K matrix. So U equal to minus Kx or minus Ky, depending on whether you have full state information or not. And then you directly try to find the K rather than estimating the system parameters followed by K. And I think a number of people here have worked on this problem. I'm interested in something intermediate, problems that are closer to what Stephen and I used to do, which are communication networks or networks with lots of queues and they're interconnected by some kind of a network. And these kind of problems, you have countable state spaces, meaning that they are not uncountable like the traditional control theory problems, although I think this is control theory in my opinion, because it's just that the state is discrete, actions are discrete, but everything else, the dynamical system way of thinking about it is the right way to think about it. But it has much more limited structure. It doesn't have the xk plus 1 equals axk plus buk form, but it does have some interesting structure. For example, if you think of a system of buffers connected by links, the buffers are all non-zero. That's one property. And the second thing is these systems are relatively easy to stabilize. What do I mean by stabilize? I don't necessarily mean asymptotic stability where you try to drive everything to zero, but it's very easy to make sure that the system, a state doesn't blow up to infinity. That's what I mean by stabilizability here. So the stability, by that I mean boundedness with probability 1 is something relatively easy to ensure. What is much harder to do is to design a controller that gives you good performance. Okay? Design an algorithm that gives you good performance. Again, I sort of interchangeably use controller, algorithm, protocols. It's just funny to me that I've always heard of it as a controller. When I went to Bell Labs, people used to call them algorithms and protocols, and for the first few years, I was actually very confused. What's the difference between all of these? And then I realized they're all the same things. So designing a good algorithm or controller should exploit some properties of the system. And this thing in the middle has more limited structure than typical control systems, but they have more structure than chess, for example. And I want to see how we can exploit the structure and what are some good abstractions to think about these kinds of problems. So motivation clear? Okay, so we finished this paper day before yesterday. I spent 8 hours preparing this talk, and I haven't looked at it since because I got here at midnight. My plane had mechanical issues. So please feel free to stop me because I might forget to say something that I meant to say. So please feel free to stop me at any time and ask questions. Yeah. So an example of a problem that arises here, which traditionally people used to call it a switch inside an internet router, but now Cisco and other companies are building giant switches that act as switches for data centers. So you can think of a switch as a matrix of queues. I mean, you don't need to know much about it other than it's a matrix of queues that contain packets, for example. And the packets are arriving to each of these queues. And the control that you have is at any one time in this matrix of queues, you can remove one packet from each queue, one in each row, one in each column. Okay, so that's the constraint. So you can't at the same time, you cannot remove packets from all of the queues in a single row or all of the queues in a single column. You can only touch one row or one column. This is a technological constraint. We don't need to go into why there is such a constraint. So this is a classical problem. I think Nick McEwen studied this in the late 1990s, and it's one of the first successful internet companies. He sold it for $400 million or something like that. And I thought the problem was dead, but in the last 5 to 10 years, it's come back because people are trying to take small switches and build giant switches, and this problem has resurfaced. So different people like to think of it differently. As I said, you can think of it as removing one packet from a buffer in each row and each column, or you can think of it as a bipartite graph, where if you put the rows on the left and the columns on the right, then basically you're so this, for example, means that I'm removing a packet from the second row and the first column, which would correspond to this. So you can represent it as a bipartite graph, or you can also, for people, since this is a CMS department, some computer scientists, so you can also think of them as permutation matrices, where you have your basically zeros and ones, and this, you can have at most 1, 1, and 1 in each row or each column. A second application, which has also come back somewhat interestingly, and now this has become a much harder problem than it used to be, is in wireless networks due to this concept called virtualization. In a wireless network, what happens is that you have a base station trying to transmit packets to different receivers, and you have to make a planning decision over the next t time slots. Your control is your planning decision over the next t time slots. where you have to decide on the F frequency slots and T time slots, and you have to decide which users' data you're going to send in each frequency time slot. This is a very challenging problem, and I don't think that there is a solution to this. This is a very interesting problem at the sort of the intersection of control, probability, and combinatorics. So you have to fill up this matrix, and there are all kinds of constraints. So for example, AT&T might have a contract with Tesla saying that, in every frame, this is called a frame, in every frame I'll give you 10 frequency time slots. It might have another service level agreement with the police force, for example, saying that, I'll give you 8 frequency time slots in every frame and so on. So these agreements are written and they're signed by the company and the people using it. And then, of course, within the police department, there are multiple police cars using this, multiple Tesla cars are being over the air. They're what do you call them? You get updates, software updates, and so on. And so you have to somehow make sure that you have minimum slot requirements to each of these companies that you have signed an agreement with, and also make sure there is some kind of a fairness. I mean, you don't, because these frequency time slots are very variable capacities. Because it's a wireless network, sometimes you can send, X number of bits. Another time you might be able to send 2X number of bits or 10X number of bits. So you have to make sure that you keep changing how you allocate slots to people so that some fairness is maintained while making sure that you satisfy your service level guarantees to the different users. Yeah.
You said that the problems become harder now than before. What made it harder?
For one thing, the early problems when Qualcomm implemented this in the mid-1990s, there was only one frequency, or many frequencies, and there was no concept of virtualization, in the sense that all the users were treated the same, and there's a beautiful solution to this by David Shea called proportional fairness, which allocates resources fairly. Now, the service level agreements, or virtualization agreements, which basically say that I have to give you so many slots. Okay, the agreement is in the level of slots, but you can't, if I keep, so let's say I agree to give you 10 slots, but if I always give you the 10 poorest slots here, because each of the slots actually has different capacities, okay, and you could be in a poor part of the network where your connectivity is poor, but I have to make sure somehow that when your connectivity becomes better, I have to switch you to the better slots so that on average, you get good service. And so there is a combinatorial element because it's now become a matrix level packing problem, along with the traditional understanding of wireless communication, fading, and all that. And this problem has become much harder. So you can't, for example, I don't think you can write down the proportional fair solution for this very easily. For the other case, it's actually a closed form solution.
Thank you.
Sure. And this is a cool example. This is something that's happened in the last 10 years or so. Matching markets. So many people from our community and the operations research community, CS community, have now spent time at Uber. One of the latest people I talked to about this was Amin Saberi at Stanford. So he actually designed the latest surge pricing algorithm for Uber. So there are 3 control actions that you can perform here. So on the left are queues of customers. Maybe this is an airport location. Maybe this is somewhere else. Maybe some places are just distributed throughout the city. So there are customers waiting. And on the right, there are Uber drivers willing to serve them. And you can decide which customer you match to, which driver. You can also control the price. Apparently now Uber has split the pricing and the payment. It's no longer what you pay is not proportional to necessarily what the driver gets. So you can control the price to reduce for example, the rate of customer arrivals or increase the rate of customer arrivals. Similarly, you can control the payment. The more you pay, there'll be more Uber users willing to take the customers. And this is a way to control the delay in the system. So the Uber platform or the Lyft platform is interested in maximizing revenue, but making sure that customers don't have to wait. So this is a trade-off. So by controlling the price, you can control the arrival rates. Of course, to make the delays 0, you just choose infinite price and zero payment, but of course then you won't make any revenue, right? So this is the trade-off. So 3 things you can control, and the goal is to figure out how best to control it to maximize revenue minus some weighted function of delay. Okay? Let me see how much. Yeah, so there are other applications too. I won't belabor the point. So I think there's a nice paper by Mohammad Alizadeh, if anybody's interested in, who looked at cloud computing problems where you have very complicated jobs that have to be scheduled on Facebook's cloud or something like that. I can't remember which particular company he worked with. And these problems are also, so the difficulty in these problems are that they all have this structure where the number of people waiting in the system can grow to infinity, okay? Potentially, of course. It's in practice, there's always some finiteness in the system, but I'm going to appeal to Stephen to say that we should ignore that, because if we don't ignore that, we won't get good algorithms, okay? And everything that I say is also true if the state space is massively large, but finite, okay? So the kind of problems I'm interested in are problems where I have a dynamical system. Sk plus 1 is f of sk, ak, wk. The state typically in all of these problems is a vector of q lengths, okay? As I mentioned before, these q lengths are positive or non-negative, and the state evolution is determined by that function f, which we don't know, okay? This function f is unknown. And our goal is to find a policy, a feedback policy. So we have to find a control algorithm, which is basically who to match to whom, okay? So there are also interesting things. You may not want to match somebody immediately because there could be some other person who comes up immediately afterwards who can be a larger fare, or maybe you have to travel a shorter distance and so on. So it's a very complicated problem, right? And the goal is to minimize, let's say, I'll just keep it simple in this case. Let's forget about prices and payments in this example. Let's just say price and payment are fixed, but all of that can be incorporated. And the goal is to minimize the total waiting time of customers. And by something called Little's law that many of you may know, it's equivalent to minimizing the total queue length in the system, okay? So I'm interested in a traditional stochastic control problem. You have a dynamical system, you have a cost, and you're interested in minimizing the average cost. The only difference between control theory, as I learned it, was that S and A are discrete here, and they're no longer continuous quantities, okay? So it's a countable state space system as opposed to an uncountable state space system. Okay. Okay, so the only notion that I'm going to introduce that you have to remember is this thing called relative value function. You can think of the relative value function, let's not go into the definitions and so on. So it's a total accumulated cost. So let's say you start in state S, and if the system is stable, it'll hit 0 at some time, okay? The total accumulated cost is called the relative value function. Okay, so if you're given a policy, different control policies will lead to different relative value functions. And it turns out that the relative value function is a really nice quantity that allows you to come up with the optimal controller. The problem with just looking at the average cost is the average cost is a number. And it's not associated with a particular state. Whereas this is associated with a particular state. Start from a particular state, see what is the total cost that you accumulate at till you hit 0. And this turns out to be, learning this is the correct thing to do to find the optimal controller. Okay, so this is the basic result in stochastic control or Markov decision processes. The standard algorithm that you're taught when you take a first course in stochastic control or MDPs is what is called policy iteration. Let me start with the bottom box. So you fix a policy, and then you try to compute its relative value function. How long from each state, what is the cost accumulated till you hit 0, okay? And that satisfies this equation, and for those of you who are traditional control theorists, this equation may not look familiar, but it's actually the same as the Hamilton-Jacobi-Bellman equation. So if you take the continuous time continuous time equivalent of this. This becomes the Hamilton-Jacobi-Bellman equation. And it was actually, Poisson studied this in the context of the physics of heat, not in a probabilistic setting. So this is called Poisson's equation in mathematics. And you solve this equation to get the relative value function. Of course, to solve this equation, you need to know the system dynamics, which is something that we don't know, right? Then what you do is, if you have the relative value function, you choose the action that maximizes the relative value function at each state. That's it. That's the optimal solution. So it turns out that you can just iteratively do this. You start with some guess for pi, for the policy, compute the relative value function, use that relative value function to compute a new policy, and you keep doing this, and this gives you the optimal solution. Okay, this is what I was taught in 1987 or whatever when I took this course. Sorry? It's Q. It's Q. Yeah. That's because if it is J pi, you cannot compute. Huh? J pi is the average cost. Sorry, J pi is the average cost, and I don't want to. If I just compute J pi, then I can't figure out what I should do at each state. So you can't get a feedback policy. So you compute Q instead. Is that clear? Yeah. So it turns out that you don't need to compute J pi. It's better to actually compute from each state how long, what is the total accumulated cost to hit 0. And that actually is the right thing to use to figure out the optimal policy. That actually minimizes J pi surprisingly. That's the theory. So now to do this, we need to know the transition model. We need to know the dynamics of the system, and I don't know the dynamics of the system. So what I have to do is to estimate this from data, and you collect samples from trajectories. Of course, in a countable state-space system, you cannot visit every possible state and every possible action. So somehow you have to do this. You have to collect samples from a trajectory generated by each policy and estimate Q. And then once you estimate Q, you don't want to use this, surprisingly. You don't want to use this algorithm, because if you use this algorithm, you'll get a deterministic policy, which means that you may not be able to explore all states and actions in the system. So you deliberately randomize the policy, that's an approximate minimization, right? If eta goes to infinity, so the new pi is the old pi multiplied by e power minus eta times Q. Okay? So which basically means as eta goes to infinity, you'll put all your weight on the minimum of Q hat over A, right? But if eta is not infinity, this is a probabilistic algorithm. So and this allows you to explore different portions of the state space. Okay? So this is a very well-known algorithm called the natural policy gradient algorithm. It's one of the most widely used algorithms in practical RL. I mean, not exactly this algorithm. There are versions of it called PPO and TRPO and so on, which are very closely related to this algorithm. This version is, it's like taking Stevens' algorithm and building fast TCP. So you take this, and then you convert it to PPO and TRPO and so on. So here's the first abstraction that I want to introduce. I mean, I don't want to study the details of this algorithm. I mean, who cares, right? There are lots of, this has been studied, how to do this very, well has been studied. So what I want to do is first, I'm going to assume that the true Q pi, of course, cannot be estimated. So I'm going to assume that we can estimate an approximate Q pi such that the infinity norm between them, meaning that over all states and actions, I have a bounded error kappa. This is not a very good abstraction, and depending on the time, I'll tell you how to fix this. But this is the abstraction that I'm going to go with, okay? There's one small modification that you have to do to this abstraction to make it much more reasonable, and then you can get, then it's easier to connect it to neural networks and universal approximation theory of neural networks and so on. Okay, so why do we need, first of all, an abstraction? Because Q cannot be estimated. So you cannot visit all states and actions in the system. So what you do is that you visit a few states and actions, estimate the Q function for those states, and then use a neural network to generalize it to all states and actions. So you train the weights of a neural network by getting data from a few states and actions, and then generalize it to all the states and actions. Now, whether that gives this function approximation error is something, there is a small issue here, but I will set that aside for right now. Okay. And the result that was known before our work is that this algorithm, the algorithm that I presented before, the natural policy algorithm, policy gradient algorithm, has a regret of square root of t. If you run t iterations of this algorithm, then the average error that you have is of the order of 1 over square root of t. Okay, so it goes to 0. But it depends on Qmax. Qmax is the largest value that Q can take over all state action pairs. And of course, if it's a countable state space system, this is infinity, right? Or even if it's super large, this is super large. And so this won't work. Okay? So, but nevertheless, let's try to estimate what the Q function is going to be. There's something called a Q function and a V function. They differ by a constant, so let's just don't worry about what Q and V are. Think of them as roughly the same at this point. So let's look at a Stevens-style fluid intuition to understand what the Q function is going to be, or the relative value function is going to be. Think of a simple Q with arrival rate lambda, departure rate Q, and let's say you start with an initial Q length of S1. So what would be the total accumulated cost in the system if it is a fluid? It'll be proportional to S squared, right? Because the amount of time that it'll take to hit 0 will be proportional to S. You're starting with S, integrate it, you'll get S squared. It's a very easy calculation. So it's 2 lines, and you can probably all figure it out if you write it out. So you just take a fluid Q, and then you see that the value function, the relative value function should be proportional to the length of the queuing system. And this is, the relative value function for each state is proportional to the square of that state, okay? But this crucially relies on the notion that the system is stable. And this could be problematic for some systems, but we'll get to that later. So the Stevens-style intuition not only tells you that, I mean, this should be expected, that the Q length, the maximum of this over all S and A will be infinity, but it even tells you what is the rate at which it goes to infinity, and this is very useful. Okay? The Stevens-style intuition tells you that this is blowing up to infinity in a quadratic form. Okay? And this is very, very important to fix this algorithm. Okay? So what is the fix? This eta that you have here, this is an approximate minimization. It's not a hard minimization. You can call it a soft min. People call it, in reinforcement learning and all of machine learning, people talk about maximizing rewards. I just always get confused by this because I always start to minimize cost. So everywhere there's a minus. So I'm going to stick with it, and since it's a friendly control audience, I'm going to minimize cost rather than maximize reward. So I'm not going to talk about soft max, I'm going to talk about soft min. Okay, so that's the soft min operator, which everybody probably has heard of the soft max operator. This is the soft min operator. Basically, it's an approximate minimization. As n goes to infinity, it is an exact minimization. So it turns out that eta is actually something, it is exactly a step size. In a Stevens connection between Lagrange multipliers and Q lengths, there is a step size parameter. It's exactly the same as this, except it's in some weird dual space called the mirror space. So for those of you who know what mirror descent is in optimization, it's actually related to that. So you can't choose step sizes arbitrarily large, right? They have to be chosen sufficiently small. And it turns out that the correct way to choose the step size is 1 over Qmax, and this is what creates the problem. Okay? So our solution is actually make the step size state dependent. Okay? Why choose a step size that's the same for all states? Okay, you're estimating the Q function for different states. And this is, again, I feel like I credit my background, Yashashwini's background in control theory for this, and Izzy's. Is you take, you shouldn't, we always like feedback. And if you know that you're in a particular state, you should use that information, right? Let's use that information. So basically, I'm going to make eta a function of the state. And then it turns out that you can show that choosing eta inversely proportional to the relative value function at that state fixes the problem. That's it. So if you try to use the eta that you need a single eta for all states, then you need eta to be smaller than 1 over Q max, which is infinity. So therefore, eta will become 0, and the system will, you can't do any minimization here, because the right-hand side is just going to be uniformly choose all actions. But this small fix, this idea that we all know from control theory, feedback, I mean, you got to know, if you're in a particular state, use that. And that eliminates the dependence on Qmax, okay? And to do that, we need to figure out what is the value function at each state. Okay, so what is the relative value function at each state? So I'm going to choose eta at each state to be inversely proportional to the value function at each state. And so to do that, I need to have an estimate, and this is where I'm again going to appeal to control theory and structure, problem structure. Queuing networks are easy to stabilize. Unlike traditional control systems, queuing networks, it's easy to stop them from blowing up to infinity, okay? In particular, it's easy to come up with algorithms which satisfy the Lyapunov drift condition, okay? So what we'll assume is that the class of policies that we'll consider are those policies that satisfy a Lyapunov drift condition. That's it. And this makes a lot of sense in practice too, in my opinion. When the system becomes large, you're not going to worry about performance. You just want to make sure that, you know, if you're an Uber or Lyft company, you want to make sure people get to their destinations quickly. So stability is absolutely important, right? So we'll give up some on performance by restricting ourselves to controls of this form, but by doing this, you have robust stability. I mean, this is a John Doyle type term, robust stability. It shouldn't matter, independent of the parameters of the system, you want stability, and this can be done in queuing networks, cannot be done in other types of dynamical systems. In queuing networks, you can do this. So as an example, what would I do? So I have about 15 minutes. So an example of an algorithm that stabilizes many types of queuing networks is what is called the max weight algorithm. So in this example, you have to choose a matching and a bipartite graph at each time step. And let's say that's the, so if this is a Uber or Lyft kind of example, the queue length, the numbers here represent the sum of the number of customers waiting on the left side and the cars waiting on the right side. So that could be maybe one customer here and one car here, okay? And maybe two customers here and three cars here and so on. So there's a weight associated with each edge, and you select the edge. In this case, one doesn't make sense, because if there's one, then you can't match some left to the right, but ignoring that for a second, because that can be easily fixed, you try to find the maximum weighted matching in this graph. And this turns out to be a maximum weighted matching in this graph, okay? If you do maximum weighted matching, the system is automatically stable, but it won't give you good performance. So what our suggestion is to use max weight matching when the queue lengths become very, very large. All of this can be quantified. And otherwise, try to use learning and control to find the optimal controller. This is the basic idea. So there is a trade-off between performance and robust stability here. I'm giving up a little bit on performance by restricting myself to a class of controllers which are like this. I'm not restricting the class of controllers when the queue length is small. When the queue length becomes very, very large, I'm saying let's use something like max weight. I mean, that just max weight is for this example, but for many queuing systems, you can find other algorithms that make sure that the system is stable. Yeah?
So you were trying to tell us that there's a trade-off between performance and robustness?
That's exactly why I'm saying it here. No.
That's interesting. Yeah, we'll talk about that later.
Yeah. This is something that everybody should do. People just optimize all the time, and I think it's silly, and I think robustness is fundamental. We know from LQG versus H infinity, it's like that, yeah. So you try to satisfy, so this is, I mean, let's forget the math here. So the basic idea is that if I assume that the system is stable, then I can get an estimate on the relative value function using the Stevens-style fluid intuition, okay? That immediately gives you that it should be quadratic. The precise proof is complicated. This is what I'll talk about at the very end. It requires a lot of connections between Lyapunov theory and the solution of Poisson's equation for Markov chains and so on. but I think this intuition is the key. And I feel like there must be a proof or a model for the whole system that doesn't require much of the mathematical complications that we used in our paper. I'll talk about that briefly at the end. So the reason, basically, what we are saying is that when the system size is very, very large, pull it towards the origin. If it is not too large, then try to find the optimal controller. Okay, this is the basic idea, which means if you're very, very far, then at a quadratic, then the relative value functions or the total cost that you accumulate will be quadratic up to this point. And then it'll be something here. And the messiest part of the proof is to figure out what happens in this part of the state space. And we want to get a policy-independent upper bound. So because I want to choose my step size independent of the policy, because I cannot choose, the policy is being learned over time. At each iteration of natural policy gradient, you get a new policy, right? The policy is just too complicated. I mean, it's something that describes a mapping from states to actions, and the number of states is infinite, so you can't make a policy-dependent step size. So I have to come up with a policy-independent step size, so I need a policy-independent bound here. And for that, I'll use more structure of queuing systems. Maybe I'll skip this part. But basically what the, okay, so maybe I'll just briefly mention it. So the main assumption that we make is that in these kind of systems with non-zero probability, you can go from some bounded state to the origin in a finite amount of time, which again in a fluid queue it's obvious. So if the arrival rate is lambda, departure rate is mu. If you start at some state S, then you'll get to the origin in 1 over mu minus lambda time. And this is essentially what we are using, but you have to use a probabilistic version of this to get a bound on the value function. And this is this kind of bounds have a long history in probability. There's a famous paper by Peter Glynn and Sean Main in 1996 who obtained bounds for the relative value function, or which is also called the solution to Poisson's equation. But their bounds are policy dependent. One of our key contributions is to make, using the special structure of our problem, why throw out the structure we have, right? Using the special structure of our problem, get policy independent bounds. Okay, so the key result in the paper, the key technical result in the paper is a bound on the relative value function, which is quadratic. And as I said, you can easily understand it by using Stevens-style fluid arguments. Here's a probabilistic answer. But the important thing is this is state dependent, so we can use it in conjunction with feedback, but it's policy independent. Okay, so that is the critical part of the result. So going back to our algorithm, I'm going to fix eta and make eta a function of the step size. And it turns out that up to a function approximation error, you get square root of t, that Qmax has gone away now. Okay? And what do I mean by a function approximation error? Actually, because of the fact that you cannot estimate the Q function exactly, and it has to be approximately estimated using a neural network, there will be an additional term here, which is kappa tau. And so if you divide by t and let t go to infinity, there'll be an error kappa. So this error kappa can be driven to 0 by using larger and larger neural networks. This is why you have massive neural networks that are being used, but of course that's not practical, so I'm not going to get into the details of that. But basically there is assuming neural networks, given a few example relative value functions for several states, generalizing to all of the state space is what neural networks do. If they can do it well, then this error, the performance error will be small. But in our case, in any case, the system is, at least it won't blow up to infinity. We know that. As a sort of okay, maybe I guess I have till 9:30, so I'll wrap it up. So that you can make this function approximation error better by knowing something more about how neural networks approximate functions. Neural networks approximate functions over a continuous functions over a compact set well. But what we have is a function that blows up to infinity. Q of S is a function of S. It's proportional to S squared. So neural networks cannot do this. So there's some additional things that have to be done. But all of that can be at least partially taken care of. There is some additional work here. Skip all of that and then go to the conclusions. So the main message here is that exploit problem structure, even if it's limited problem structure. I mean, we don't have the xk plus 1 equal to axk plus buk plus wk here, but there is limited problem structure nevertheless. Queuing networks are well behaved in some ways, in many ways. It's easy to stabilize them often. And so you should design RL algorithms to control countable state space applications like communication networks, cloud computing, ride sharing, and all that by exploiting the problem structure. Even though it's limited, using that limited structure is actually very, very important, not just throw reinforcement learning blindly at it. Our results hint on fluid intuition, but the mathematically rigorous proofs require discrete probabilistic arguments. But I do believe that a purely Stephen Low style deterministic optimization theoretic model and proof may be possible here. And here are some reasons I strongly believe that. One is replace discrete actions by the fraction of time you're taking an action. That's the way to naturally make something that's discrete into a continuous object. The second thing is policy optimization is very closely related to this algorithm called mirror descent. Mirror descent is a way of doing gradient descent in a different space called the mirror space. This is a beautiful idea by Nemirovsky and Yudin. And this is a different type of duality, not the Lagrangian duality exploited by Low and Lapsley, but it's a different type of duality. But I do believe that we can just, so you can view this algorithm as a solution to some optimization problem. I still haven't figured out how to construct that optimization problem in a manner that's amenable to an analysis like this, but perhaps this is a future topic for future work for all of us here. And I want to conclude by saying happy birthday again, Stephen. It's been a pleasure knowing you as a friend, colleague, and an inspiration for many, many years, and I hope to continue to learn from you for the next several decades. Thank you. Yeah, constrained MDPs are also well studied. So there, actually, a Stephen-style analysis would immediately work. Constraints can be added to the objective using Lagrange multipliers, and then we can, of course, there are going to be details, I mean, lots of details, but that's the way I would do it. So you can append them using Lagrange multipliers, or there are other ways to impose constraints in MDPs that you could, I can impose them in the learning process. That's a good question, yeah. Thanks.
Thank you, Srikant. So one question about the technical question. So you had an assumption on the Q approximation arrow is the infinite norm.
Right.
Like how the result would be depending on that. If I change the infinite norm to be like the L2 norm or the Lebesgue measure.
That's a good question. That's a good question. I don't know. Actually, maybe relaxing it, maybe a different norm might actually make the analysis simpler. It's possible. Ultimately, part of the proof involves getting a bound on the 2 norm of the Q lengths. If that assumption is also made on the 2 norm, then it's possible that it might make the proofs simpler, but I have to think a little bit more about how that connects to neural network realization theory.
The reason I'm asking, but we can talk more offline, is when retracing back to those NPG, those algorithms, and also Q approximation, you're familiar with those linear MDP, you had those kind of papers.
Which one?
Linear MDP representation,
linear MDP,
right?
correct,
So because back to the question for the representation, if I use the representation starting from my P kernel transition. And then that arrow, like making any kind of
Actually,
assumption.
I wanted to talk to you about this. I have a question
Yes.
about this very specifically. I know you worked on basically
okay.
converting every MDP to a linear MDP.
Yes.
I guess my question is whether that will work for infinite state spaces, not in a bounded set. If the state space is not in a bounded set, I want to talk to you about this. Yeah, we talked about this at MIT once, and yeah, I'll ask you this question practically. Yeah, and there's one last question here, maybe Harvey.
So I wanted to ask, but it's really the start of another conversation about real complex systems. So, for example, the inputs to the optimization objective function are classes of variables which are very different in character. There's a characteristic time in the dynamism of the system which you have to compare to your time to convergence. And then there are constraints, and immediately you come to this transition to game theory because the systems are too complex, where you can only evaluate your level of success by how happy people are. And so I'd like to start talking to you about those things.
Okay. Yeah, there is a sense in which I was talking to somebody else recently, and I can't think of. Oh, Anna Busich, who's a applied mathematician in France, and she mentioned this, and other people have also thought about this, is to think of the platform as a mechanism designer. So a platform is something that shapes how drivers and customers react, for example. So depending on Uber's policy, I'm not taking that into account. That makes it very, very complex. The pricing and payment policy, I'm assuming very simply that it just controls the arrival rates. It could be something much more complicated than that. Thinking of a platform as a mechanism designer is a challenging question. I'm sure Eric Mazumdar probably knows a lot more about this, and I think I'm planning to talk to him sometime later today. But yeah, that's an interesting work, and I guess Eric and Adam have joined postdocs Zaiwei, who sort of looked at reinforcement learning, game theory, and all that. So I think there's a lot of interesting connections here. Yeah, thank you.
Okay, let's thank Srikant again.